We are going to head into 5.4, which is dealing with the second derivative now and what we call concavity. In 5.3, to recall, what we looked at was the first derivative and how did the first derivative help us make decisions about what was happening with our function. Now what we're going to be doing is using the second derivative to be telling us things about what our function is doing. So if you look below, there are those objectives. These are the things that you should be able to do by the end of the lesson. To get into this chapter, what I'm going to just look at is this model. We're going to start with a quick review on what the first derivative told us, and then we're going to start getting into, well, then what does the second derivative tell us? So we're going to look at if a ball was tossed straight up into the air. We're going to represent the height of it by this equation right here, where this is the acceleration of gravity, this was the initial velocity, and this was the initial height. In the last chapter, we really started looking at what is the instantaneous velocity of a projectile motion function. So what is the instantaneous velocity or speed of this ball that's getting tossed up? So right down here I have that table of values. I've derived the original function, the displacement function, and now what I have here is the equation that would give me the velocity at instantaneous moments. I hope this one really makes sense. At time 0, well, that's that instant that you let it leave your hand. That's that oomph that you gave it. That would be 40 feet per second, because that matches right here. That was your initial velocity. Another interesting point would be right here. That is the critical value. It's at about 1.25 when that ball, pretty much the velocity, it stopped. The speed was at 0 for that moment. And what it did was it switched from going 8 feet per minute to -8 feet per, and I should have said second. So I mean, it switched at that critical value. When we studied the last chapter, we were looking for those critical values. Where is our first derivative equal to 0? Because at that point we have what we call the critical value, and that was the potential points at which the derivative would change from positive to negative, or negative to positive, either one. But what we were finding out was that that first derivative would tell us where the original function was increasing or decreasing. All of those derivatives were positive. That ball was moving in the positive direction. I'm going to go ahead and box that there. And all of these, after our critical value, what we had was a negative rate of change, or in other words, the first derivative was negative. So that indicated where our slopes were negative, and how we interpreted that, or how we learned to interpret that, was that would translate to our original function as a decreasing. I've cleared all my annotations, and what I want us to look at now is the first derivative. All of these rates of changes, what's happening with them? It's definitely not a constant rate of change. It's like this ball was flying up in the air, right? And he's a happy ball looking upwards. Yeah, he's looking up. But then all of a sudden he gets to the certain point where gravity starts to bring him down. And it's slowing his speed down. So at the start he was going 40 feet per second. But then you'll notice his rate of change is slowing down, because he's going now 24 feet per second, then 8 feet per second, and then he actually didn't have a velocity. It was considered a 0 velocity, and then what happens is he starts to go in the negative direction. So I mean, that's going to be a negative velocity. As we move down along this XY table, or in other words, as we work in the positive direction along the x-axis, what we're noticing is our rates of changes are slowly, or I mean gradually, decreasing. What I'm going to look at right now is our second derivative, h double prime, which would of course be taking our first derivative and deriving that. That's what we get as a result. And so basically what I found, and it sounds confusing, but just kind of think of it for a moment. What we found with the second derivative is the rate of change of the rate of change. And when you study this XY table, going down like that, what we can see is it's this constant of a rate of change of negative 32 each time. And that is gravity. The acceleration of this ball is negative 32 because gravity is pulling down on it. And what that resulted was decreasing rate of change. So just kind of chomp on that for a second. So I just have a quick visual. I'm going to keep this as simple as possible. Let's say I have a function that looks something like this. We'll call it f. Alright. If we were to start picking points along this function and graphing the tangent line, note that one's a very steep positive slope. Alright. So we could say that that's something like 20, a slope of 20. Here, if we were to draw the tangent line there, it's not as steep, so it's, maybe about something like 15. Here, if we do get to one of those critical values, we have 0, and then so on and so forth as you draw these lines. So just looking at these, up until that mark that I just drew last, when you're looking at these, I hope you can realize that as we are moving along the x-axis in the positive direction, what was happening with that rate of change was it was decreasing. So we had a decreasing rate of change. That's similar to what we were looking at in the slide before this with the ball that was thrown up into the air. I'm going to kind of X an important key point. This point we're going to begin to recognize, but I'm going to switch colors now because it's at this point we're going to say that all of a sudden, as we're drawing tangent lines to our function past that now what's happening is the rate of change of our function now is going to be increasing. So in other words, the rate of change of the rate of change is positive. What we call this piece right here, this was what we call concave down. It's like if you drew a cave, it would open the normal way, it would open down. So concave down versus this section right here, starting at this X, that's what we call concave up, because it's kind of like a bowl is facing up, bowl up. So what we have are concave up, I never finished this, this is concave down, and concave up. So kind of a rough sketch, but what we're eventually going to find is when we were looking at that original model, so this one right here, when we were studying this, we're trying to study our rate of change. We're trying to figure out, is our rate of change increasing or is our rate of change decreasing? So just like we used the first derivative to tell us what our function was doing, we're looking at the second derivative to tell us what our first derivative is doing. And what we're going to be switching now to is our second derivative will tell us if it's concave up or if it's concave down. You do have the formal definition on page 338. Here is my kind of informal. I'm going to let you take a moment to write that down. What we're really looking for is now the second derivative. We're looking at the second derivative. If that's negative, that tells us that the rate of change of our function is decreasing. Basically what I want you to know is this. If f prime of x is negative, if f double prime of x is negative, then what we have is concave down. It's something that's in the concave down form in the original function. And then when the rate of change of a function increases, so in other words, when f double prime of x is positive, that means that the first derivative was increasing, which would indicate to us concave up. It's going to look something like this. Alright, and the point where the rate of change changes from increasing to decreasing or vice versa, that's what we call the point of inflection. Just to distinguish again further what we did yesterday versus what we did today, before what we were looking at is when our function was increasing, we would be able to tell if the first derivative was positive. Okay, so in other words, greater than 0. Versus what we're doing today is we're looking at the rate of change. So we're looking at if the rate of change is increasing. So not the function is increasing, but the rate of change. So the first derivative If the first derivative is increasing, that's going to be when then the second derivative is positive. So it's one step further than it was up here. Right? But this is going to tell us it's going to translate back to our original function as concave up. All right, and then again for same thing for this. Function is decreasing. The original function was decreasing when we looked at the derivative as negative. We're not going to be looking at the function itself. We're going to be looking at the rate of change, whether or not that's decreasing or increasing. And so therefore we're going to have to look at the second derivative, and that's going to tell us when it's concave down. All right. To drive it even further, I want you to look at the difference between yesterday and today. I'm going to go ahead and mark. We're going to make some key points. We're going to look at critical values and mark them with points or little dots. All of these graphs demonstrate with the red line an original function, and the green line demonstrates the derivative. So it's the graph of the derivative. So I'm going to look at this red line, and I'm just going to pick out some of our critical points. Where are things that are interesting going on? And basically I'm going to draw a point here, and I'm going to draw a point here, because those are interesting points to us. Those were the potential places where the function was changing from increasing to decreasing, or decreasing to increasing. And at those critical points, what I want you to recognize is they align up where f prime of x is equal to 0. Alright, I want you to look over here. Same thing. If I were to look at this as my critical point, once again, that aligns where f prime of x was equal to 0. So where f prime of x is equal to 0. Sorry, and also here. Alright, and then I'm going to now look at what we're focusing on today. Because now what we're focusing on today is where f double prime of x is equal to 0, because that will be indicating to us the changes where our derivative is increasing and decreasing. Okay, so it's not where the function is changing from increasing to decreasing, but where the derivative is changing from increasing to decreasing. So in other words, the humps and the valleys of our derivative. And if you look at all the humps and valleys of our derivative, what I can tell you is those align with very special points in our original function. Because if you look here, that was concave up, now it's concave down. If you look here, right at that point, it was the valley of our first derivative. That's where we changed from concave down to concave up. All right, over here again, I'm going to pick out those places where the first derivative had a hump or valley. So it was basically the critical points of our derivative. And these are what we're calling those inflection points. Okay, over here, same thing. If I were to look at my humps and valleys of my derivative, so in other words, where my derivative was changing from increasing to decreasing, or vice versa, what that translated to on our original function was the places where, and sorry, this is going to be right over it, and right here. Oh. Gosh, it does that sometimes, sorry. But those x's mark the inflection points. If I follow this along, there's concave up, concave down, concave up, concave down.